All right, so we're going to kind of speed run this and go through our targets. So if we start first with our toolkit for the unit circle side. So the central boxes are meant for the degrees, the middle boxes are meant for the radians, and then the outside is meant for your angle or your coordinate points. I am okay if off to the side you write, if you color-coded things like which ones are which. So blue boxes are degrees, orange boxes are radians, green boxes are coordinates, and then the x-coordinate is cosine, the y-coordinate is sine. That's fine if you want to put that off to the side here, but that would be the only thing I would expect to see off to the side on this side of the toolkit. So hopefully you already have this all written down, but just in case you need to pause and take a look at mine, those are the values that I have. Moving on to our other targets. So we're going to start with inverse targets. This is going to be the last time you see this particular target on a test. So this is one that you may want to try and make sure that you include some information on. Keep in mind that when we're doing inverses, the first thing we're going to do is take our x and our y values and switch them. So looking at this equation, I see that it's y equals 2x minus 3 to the 5th plus 4. I'm going to flip that and make it x equals 2y minus 3 to the 5th plus 4. Because once I do this, now I'm able to solve for y, and that sets up my inverse equation. I'm going to end up doing the same thing over here too. These are just two different examples. Keep in mind that we follow our order of PEMDAS backwards. So on your toolkit, you see PEMDAS written. It says simplify goes this way, solve goes the other way. We're solving for y right now, so we need to get the y by itself. So following my order of operations backwards, I'm going to undo my adding and subtracting first. And then I'm going to undo my dividing second, so I end up with, so I undid plus 4, and then I undid multiplying by 2. That's how I got here. Then I'm going to take the fifth root to get rid of that exponent piece. Now please do not simplify these things, because you will end up with a mistake if you try and do that. So like trying to deal with the dividing by 2 and the minus 4, feeling like you can simplify that, please don't. It always ends up messy, and it always ends up with mistakes, so please just leave it the way it is. Now we get here, and we need to get y by itself. I'm just flipping around the order again, putting the y in front. You could leave it in the back, it would be fine. X minus 4 over 2. Keep in mind that that 3 needs to stay outside of the fifth root. It cannot go inside. Same idea over here. You might also see me write it as f of x instead of y, but keep in mind those are the same idea. So you can literally write it with a y and then flip your x and y, and that's totally fine. So you will be asked to find the inverse of an exponential or a logarithm. It's just going to depend on which version of the test you have. If you are dealing with a log or an exponential, you need to get rid of everything outside of that particular piece. So in this case, it's a log, so I need to get rid of everything outside of the log base 2 section of my equation, meaning the 3 and the 4 both have to go to the other side before I can do anything else. So I'm going to subtract the 4 and then divide by 3, and that gets me here. Once I've done that, then I can use what we've talked about, which is Abe to Bay, the idea of switching around your exponentials and your logarithms. Keep in mind, I use those letters on purpose. It's because they stand for things. So A stands for answer, B stands for base, E stands for exponent. So I use those letters on purpose because it makes it easier for me to keep track of what's what. So right now this is set up in Bay format. Notice the E is actually in the front instead of in the back, but that's okay. It means the same thing. So I'm going to take my pieces and rewrite them. So my base is 2. My exponent is the fraction, so x minus 4 over 3, and my answer is the x minus 1. Oh, I wrote x twice. That should have been a y. So is the y minus 1. Now that I'm here, I can finish solving for y by subtracting or adding that 1 to the other side. So I get 2 to the x minus 4 over 3 plus 1 equals y, and this is my inverse equation. Keep in mind, if you plug in a number up here, you should get out, and you get out a separate number here. So let's say I plug in 2, I get out 10. If I plug the 10 in down here for x, I should get the 2 back out. So they should undo each other. So that's our inverses target. I'm going to move on to solving an extraneous solution. So this is going to be a situation where you're going to be asked to solve for x, just finding your x value. Again, since we're solving, we're going to be following our order of operations backwards. So we're going to go SADMEP is how I always say that. So starting here, since this is a log or an exponential, I need to get everything outside of the log or the exponential, in this case an exponential, to the other side first. So I'm going to subtract my 6. So that gives me 4 times 3 to the x minus 2 equals negative 7. I'm going to divide by the 4, so 3 to the x minus 2 equals negative 1.75. You could make it a fraction if you wanted to. Once I get here, now I am ready to do the same idea, the same conversion. So this time it's in ABE format, so it's answer equals base to the exponent. And I'm going to rewrite it as an exponent, or as a logarithm. So log, in this case, my base is 3. My answer is the negative 1.75. And my exponent is the x minus 2. Then I'm going to type this into my calculator. I'm pretty sure this one is gonna end up not working out, but I'm gonna try it anyways. In case you forget how to set up this in your calculator, what you end up doing is log of your answer piece divided by log of your base. And that's going to give you some sort of decimal if this works. Once we get our decimal, then we'll be able to add the 2 to the other side. So in my calculator, I'm going to do log of negative 1.75 and then divided by log of 3. And it doesn't end up working in my calculator, but that is the process that we would follow, even if it didn't, or if it does work, which it should on your test. You should be able to get some sort of answer that will include a decimal. Please round your answer to 3 decimal places. Same idea over here. We want to get our log or our exponential by itself first before we try and solve anything. So I'm going to get rid of anything that's not inside the logarithm, in this case the 5. I'm going to subtract that to the other side. I get log base 3 of x minus 8 equals 2. And now I can convert from Bay format, log format, to an exponential. So my answer is x minus 8. My base is 3. And my exponent is 2. So x minus 8 equals 9, because 3 to the second power is 9. And then I can add the 8 to the other side. I get x equals 17. Will these work out to nice numbers all the time on the test? Absolutely not. In fact, I would expect that you're going to get decimals here, and that is absolutely okay. So these are our first 2 targets, solving inverses and then solve with extraneous solutions. So you should then take your answers, plug them back in, make sure that they actually work. Moving on. So a huge portion of this test references right triangles and working with those different right triangles. So let's see, I just wanted to check if there was more than one target or just one target referencing this. There's only one target that references the right triangles, but we're going to see it in 2 different ways on your test. So way number 1 is your 30, 60, 90 and your 45, 45, 90 triangles, which thankfully you will see are listed on your toolkit. So you see a target like this, or you see a triangle that looks like this. I notice that these 2 sides are labeled as the same. When I see that, if both of the 2 sides in a right triangle are labeled as the same, that automatically tells me I'm looking at a 45, 45, 90 triangle. And in case you forgot, 45, 45, 90 just means that the 2 non-right angles have to be 45 degrees. So already got 2 out of my 4 answers figured out. In order to find these 2 side lengths, we can use what we know about our special right triangles. The way that we talked about this is we said that this side would be x, this side would also be x, and then this side is whatever that x side is times the square root of 2. So I can solve for x by saying whatever that side is times the square root of 2 works out to 18. And I can divide by the square root of 2 to get x by itself. So x is 18 divided by square root of 2. If you left your answer like this, beautiful. If you chose to go through the process of rationalizing it, meaning multiplying by the square root of 2 over the square root of 2, the bottom here becomes 2, numerator becomes 18 square root of 2, and then we can simplify. Either one of those answers would be perfectly acceptable. And since these 2 sides are labeled as the same, I can just carry that answer down. Looking at our other triangle here, again, what they're hoping that you notice is in our special right triangles, we said that the short side of a 30, 60, 90 is always half the length of the hypotenuse. So they're trying to reference that here and showing you that this side is half the length of the hypotenuse. That tells me that angle A has to be 30 degrees because the short side is always across from the 30-degree angle, which would mean that the B angle has to be 60 degrees. Now, in order to find our C side, or our AC side, we have the 1/2. What we're saying is we need to take that and multiply it by the square root of 3. So I'm going to take that shorter side and multiply by the square root of 3, write my answer like this. We're very particular on the test on special right triangles, so on these ones, I absolutely require that you do not use decimals, so I should not see a decimal equivalent of this. If you do, it's automatically a yellow at best. However, on non-special right triangles, so just random right triangles where I'm asking you to use like sine, cosine, and tangent, you are absolutely allowed to get decimals here, and that is totally okay. So I will list the pieces that I need off to the side for you, and keep in mind that the 2 letters represent the end lengths. You can label them if you want to, so I'm going to call these like X and Y. The easy one, in my opinion, on this first triangle is finding this angle here, because I know that the 3 angles in a triangle have to add up to 180. I can just take 180 minus 90, which is 90, and then 90 minus 19, which is 71, and that gives me that missing angle. Then I'm going to go through and use my trig to find my missing sides here. I generally like to work from the angle I was given, just in case I made a mistake on doing my math there, because sometimes that happens. So from the angle I was given, I have the opposite side. So just as a reminder, I write the SOHCAHTOA thing like this, because it just reminds me what order my fractions go in. So sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So from my angle, I have the opposite side. And we'll say I'm starting with finding the hypotenuse, so that means I'm going to be using sine. So I would set up sine of 19 degrees equals 11 over x. In order to solve for x, I would need to multiply by that x first to get it to the other side, and then divide by the sine of 19. And I can do that in a calculator. Make sure your calculator is in degrees for these problems. If it's in radians, you will get the wrong answer, which is a bummer. If I catch it when I'm looking at your test, I will more than likely give you, I would take off in MP1. So let's see. So if I do this in my calculator, I get 33.787. And then I got to find my other missing side. So in this case, again, I would use the angle I was given. So I was given the angle of 19 degrees. I have my opposite side, but I want my adjacent this time, so I would set up tangent. You could absolutely choose to use Pythagorean theorem here if you would prefer. This is a later problem, so sorry, I just didn't give myself quite enough space here. Then I would go through and solve for y, so I would multiply by y on both sides. Y times now equals 19 equals 11. Divide by tangent of 19 on both sides. And I get 31.946 for my angle, or for my side there, which, looking at my picture, that does logically make sense in terms of this picture. You would do the same thing here. Notice this one I didn't give you any angles, and I did that on purpose because you could be asked to find missing angles. Now, I'm going to start with the side because I do think it's the easy one. I could use Pythagorean theorem here, so I could do a squared plus b squared equals c squared. So I could do 100 plus 64, so this is the square root of 164, which I could actually go through and calculate if I would like to, which would be approximately 12.806. Now to find my angle measures, let's say I'm going to start with angle A. From angle A, I have the opposite side and I have the adjacent side, so I would be setting up tangent of A equals 8 over 10, and then I can use tangent inverse to find that angle measurement. So if we go and we use tangent inverse, and that will help us solve for our angle. Sorry, my calculator and I are just disagreeing at the moment, so I'm going to move on and come back and find those angles in a little bit. Okay, next target that we've got here is, let's see, so we did solve equations, we did right triangles, did inverse. So now we're moving on to unit circle things. So in the unit circle, I might give you a problem like this, where I'm asking you to find a particular measurement. So it says sine of theta equals square root of 2 over 2. What I'm asking you to do is look at your unit circle and look for where the sine value, meaning the y value, is the square root of 2 over 2. So looking at my unit circle, I see that happening here, but I also see it happening here. So both of these places, the angle measures are the exact, or what I'm looking for. So I would see both of these numbers written as my answer. And I would want you to kind of draw that in. So sine of square root of 2 over 2 happens there, happens there. So my two answers are 45 degrees and 135 degrees. There will be some cases where you only get one answer, but a lot of the time you're going to get two answers on these types of problems. So cosine, we said, is the x value. So I'm asking, where is the x value? Negative 1/2. Looking at my unit circle, I see that happening here, x value of negative 1/2, and here, x value of negative 1/2. So I would be writing 120 and 240 on the line. 120, 240. Again, you could get just a singular answer, but likely you're going to have multiple answers for those. Now, finding exact coordinates. This, again, is using your unit circle, but I'm more than likely going to give you an answer that is outside of the unit circle. So, for example, 510 is beyond our 360 degrees. So in order to find the exact coordinates, what I need to do is take my angle measure that I'm working with and take away 360 as many times as I can. So in this case, if I take away 360, I get 150 degrees. So that's no longer bigger than 360. So that means I went all the way around the circle once. And now I'm going another 150 degrees. So here, if I look at my unit circle, that 150 degrees puts me right here. I want to know the exact coordinates of this spot because this represents 150 degrees, but it also represents if I were to go 510 degrees. So this is what I would be looking for as my answer. So the exact coordinates of this particular location are negative square root of 3 over 2, 1/2. So if you can't tell, a big part of your test is going to be, can you read your unit circle and understand what we're talking about with those different pieces? You're also going to be asked to graph trig functions. So I've got two different examples here, one that is sine, one that is cosine. So the way that we always started with our trig functions is we started with our midline. So when I'm looking at my function, I'm looking for a k value. So like in this case, my k value is at negative 1. So what that means is my graph is going to oscillate around negative 1. I tend to prefer to draw in a dotted line for my midline because it just kind of reminds me like, hey, this is where I need to keep everything kind of centered around. Once we know our midline, it's at y equals negative 1 in this case, then I like to use my amplitude to help me figure out like the bounds of my graph. How high and how low is it going? In this case, my amplitude is 3. Because it comes from our a value. Once I have that figured out, I like to kind of make a little note to myself like, oh, my graph is only going to go 3 above and 3 below my midline. So from here, I'm only going to go up 1, 2, 3. Only going to go up that high. And I'm only going to go down 1, 2, 3 below the line. So my graph is only going to be within this space all the way across. After I find those two pieces, the next thing I look for is my phase shift, which is coming from your h value. In this case, I don't have an h value, which means my graph is going to start right on the y-axis. So my sine wave is going to start right at 0. This is going to be the y-axis right there. So that's helpful for me because that means that at my midline, on the y-axis, right here, is where my graph is going to start. Once I have that phase shift figured out, then I'm going to move on to finding the length of the period. As a reminder, we said that the period was always 2 pi divided by your b value, gave you the length of the period. So in this case, our b value is 1/2. So 2 pi divided by 1/2 gives me the length of the period. 2 pi divided by 1/2 is 4 pi. So the period is going to take 4 pi to complete. So that means if my graph starts here, the end, this one, is 4 pi units from my starting point. So all the way over here. Now that I've got my start and my end, that's the first point I find, the last point I find, then I always find my middle point here because it's also on the midline and it's exactly halfway in between the first 2 points that I found. So halfway between 0 and 4 pi is at 2 pi. That means my middle point is there. Now that I've got those 3 points in place, I can find the peak of my graph, the maximum point, because it's always halfway between my start and my middle and at the highest point of my amplitude. So halfway between 0 and 2 pi is 1 pi, and I have to go up 3 units. And then this point is always halfway between my middle and end, and down my amplitude, so down 3 units. Now that I've got my 5-point or my 5-number summary in place, I can draw in my graph, and we're actually going to use this picture to tag on another target because you will be asked to find the domain and range of trig graphs on your test. So the nice part is that for trig graphs, our domain is always all real numbers because this graph is going to go backwards and forwards doing this wave thing forever. So like I can extend this way, I can extend that way. It feels weird to draw arrows for that because you're like, it's not actually going in this way forever, but a lot of times you will see arrows drawn. Our range is a little bit more tricky, but actually also a little bit easy too. The minimum value that we found using our amplitude and the maximum value we found using our amplitude, that is the bounds of your range. So in this case, my graph is only going to go down to -4 and only up to 2. And I use brackets because it's hitting both of those numbers. It hits -4 right here, it hits 2 right there. Now, cosine is done in a very similar fashion. The only difference is like, where are we starting on the wave? So we're going to do this process all over again. So starting at the very beginning, we start with our midline. In this case, I don't have a k value, which means that my midline is at 0. So I'm going to be oscillating or waving around the around the x-axis. Now that I know that, I can move on to my amplitude, which we said is our a value, which in this case is 2. So we're going to be going up 2 and down 2 from that. Our phase shift is where we head next. That's our h value, which in this case we do have one. So this is saying that my graph is shifted to the left pi/4. So instead of starting right on the y-axis like we did before, our cosine graph, which looks like that, by the way, is going to be shifted backwards. Instead of this being right on the y-axis, it's going to be shifted back pi/4. Now notice this is the peak of the graph. So we're going 2 units up from our midline and back pi/4. So my graph is going to start right there. In this case, I have no b value, which means the period is exactly as normal, or the same length as normal, which is 2 pi. So from my starting point, I'm going to move forward 2 pi units. So 1 pi unit would be here, 2 pi would be there. The way you can figure that out is in your calculator. Since I know I went backwards to -pi/4 to start, I can go -pi/4 plus 2 pi. And whatever it spits out, which in this case would be 1.75 pi, is where I need to end. So I just put on this point, I put on this point. Just like on our sine graph, the middle point is very easy to find because it's always exactly halfway in between the two we have. So halfway in between -1/4 and +1.75 would be 3/4. And then it's at the very bottom of our graph. So we're going down 2 from our midline. So we just put that one on. So now we're going to do these two, which are exactly halfway in between again. And these ones will be on the midline. So now we've got our wave. And again, the wave does continue. So you could choose to keep drawing it. If you would like. The domain, just like we said, would be all real numbers. And our range will go from our lowest point on our graph, our minimum value, to our maximum point on our graph, or our maximum value, like that. You may be asked to list all these pieces off to the side. So our phase shift came from here. Our amplitude came from here. Our midline came from our k value, which we didn't have on this one, but we did have up here. Next target is degrees to radians and radians to degrees. So we used the chemistry model to kind of set this up. So we said that our conversion factor is always 180 degrees to pi radians. So degrees, radians. And just like in chemistry, the way that we set this up is kind of like that train track looking method. And whatever we put here has to be the opposite of what we had originally. So originally we had radians on top because I see the pi on top. So that means when I want to do my conversion, my pi has to go on the bottom and my degrees goes on top. Now in chemistry, the way that you did this is you multiplied straight across and then you started to simplify. So we would do 18 pi times 180. I'm going to ignore that pi symbol for a minute and just do 18 times 180. So I get 3,240 pi over 15 pi. And the reason that I chose to ignore that pi is because I look here and I see that my pi's are going to cancel. When you are converting from degrees to radians and radians to degrees, or when we're specifically going from radians to degrees, the pi symbols should cancel. So I get here, now I have 3,240 divided by 15, which I'm going to do in a calculator, and hopefully it does simplify. In this case, it does. It gives me 216 degrees. So that's our conversion. Now, if we want to go the other direction, this time I gave you degrees, and I want to go to radians, we just have to flip our conversion upside down. So because degrees is on top here, that means degrees has to go on the bottom on our next one. Just like before, we're going to multiply straight across. And then we're going to simplify our fraction. Try not to, or don't do this with the pi symbol in there. I would simplify that fraction first, get that down to a much simpler number, and then just tack the pi symbol back on. Now 34 only has one number or one factor in common with 180. They're both divisible by 2. So this becomes 17 pi over 90, and that's really as simple as this one can go. So these are our two solutions. So this is our conversion factor, converting from degrees to radians or radians to degrees, and it's just one way, or 180 over pi or pi over 180, depending on whether you want to go from radians to degrees or degrees to radians. Moving on forward. Our next target is solving systems of equations. Now you will have a linear system on there. I didn't include it because we've seen those so many times. I'm hoping you don't need a practice problem of how to deal with a linear system. It's just a 2-variable linear system, like x and y. It's not 3 variables. If I give you an exponential equation like this, I more than likely am going to set it up where the y's are, where both equations is set equal to y. What that means is I can set them equal to each other. Now, a lot of kids really freak out when they see this because they think that it's going to be a lot more challenging than it really is. You'll notice that I gave you the bases to be exactly the same. Now, if the bases are the same and they're set equal to each other, that means our exponents have to be the same, because 2 to the 3rd power can't equal 2 to the 7th power, right? Like, logically, that just makes sense. So that would mean that since these bases are the same, I can just set my 2 exponents equal to each other. Oop, that's a 7, not a 2. X minus 7 equals 3x plus 1. And I can solve this for x. So I'm going to subtract my 1 to the other side, subtract my x to the other side. I get negative 8 equals 2x, which means negative 4 equals x. That gives me my x value. Now I just need to take it, plug it back in, and get out a y value. So I'm going to go into this top equation, go y equals 2 to the negative 4 minus 7, which means y equals 2 to the negative 11th power. And I can type that into a calculator and get out an answer. Which you can write it as a fraction if you'd like, or you could write it as a decimal. In this case, I'm going to write it as both. So I would say negative 4, comma, 0.000488, or negative 4, comma, 1 over 2 to the 11th, 1 over 2048. That's our answer. This type of problem has come up on several of our last tests, and this always tends to be a struggle. Notice I have them set equal to y again, which just like up above, we can set them equal to each other. So I can say the square root of 1 minus 4x equals x plus 5. From here, the first thing you want to do is get rid of the square root, because it's frustrating to have in the problem, and we'd love to be able to get rid of it. So I'm going to square both sides, because that gets rid of a square root. Squaring and square rooting cancel each other out, so nothing at all happens to this side other than the square root symbol's gone. On this side, please don't kill puppies. Go through the process. You are creating the box, so you are doing x plus 5 times x plus 5. That's going to give you x squared plus 10x plus 25. Then you're going to go through and move everything over to one side. So I subtract the 1 and add the 4x to get here. Once I've got everything to one side, you should, hopefully, be able to factor your problem, meaning I'm going to just put this into the box. So I'm looking for two numbers that multiply to make 24 and add to make 14, which would be 12 and 2. So this factors to be x plus 12, x plus 2. So my two solutions are x equals negative 12 and x equals negative 2. Now that I've got my two x values, just like up above, we're going to plug them back in and get our y values. In my opinion, this lower one is much easier to plug into, so that's what I'm going to do. So y equals negative 12 plus 5, so y equals negative 7 in that case. And if I plug -2 in there, I get y equals -2 plus 5, which means y equals 3. I should test those points and make sure that they both work. My assumption is that one of them may not. So I'm going to plug in -12 into this top equation and make sure that I get out -7 as a y value. So if I plug in -12, I get, and if I plug in -7, I have -7 equals the square root of 1 minus 4 times -12. 4 times -12 is -48, so 1 minus -48, which is 49. This is not a real solution because technically the square root of 49 is +7 unless I actually say that I'm looking for the negative solution. So this is our extraneous solution. I'm going to check the other one too just to make 100% sure that that does work out the way I think it's supposed to. So I'm plugging in 3 for y and -2 for x. 4 times -2 is -8, so 1 minus -8 is 9, which does work out to be the same thing, so that is a good solution. So we would say there are two solutions technically, but one is extraneous, so the solution here would be -2, 3, and this one, you could list it, but you would want to say that it is extraneous. And that would be the last target on our test.